This video is the next one in the series of review things for AP Physics C, and this one is about linear and angular momentum. So I want to remind you a little bit about what those things are because they're related. Linear momentum, remember, is just going to be P is linear momentum. It's just going to be the mass times the velocity. It can be a vector also. A lot of times we just treat it as a scalar. It's going to have units that are going to be like kilograms, meters per second. Okay. And it can be conserved also. Angular momentum is really similar. It's L, and it's going to be R cross mv. And it's going to have units that have an extra meter in it. It's going to be kilograms, meters squared per second. Okay. A lot of times, though, when we just treat it as a scalar, we're just going to say mvr sine of theta, where theta is the angle between them. So if this is v and this is the radial vector, that's going to be those. If they are perpendicular to one another, then it's going to be mvr. That a lot of times describes things that are going around in a circle. So if something is going around in a circle with the speed v, and this is the distance r, you can see they're always going to be perpendicular to each other. That's going to work there. We can also express it as I omega, where I is the moment of inertia and omega is going to be the angular velocity that it's going to move with. We're going to use this, and this an awful lot. So when is only linear momentum conserved? It's a good question. Okay. Basically what has to happen is that the objects have to strike the point of contact has to be the center of mass. So like, for example, the easy one is like we got a block, it hits another block. They're still hitting like they're along this table here, right? Okay. This is like the view from the side, right? So we got two blocks that hit in there. Obviously, it's going to hit in the center of mass. The center of mass is going to strike the center of mass, right? And that's pretty easy to see. But now we're going to look from the top view. Okay, so from the top view, this example looks an awful lot like this. And in that example, what's going to happen is that momentum is conserved. Technically, angular momentum is conserved because angular momentum is zero also. So I guess technically they're both conserved, but it's sort of a trivial exercise to say they're conserved. Now, if this guy, let's say that this guy's a little bit off center, so it goes over here and it bangs into the block, but the block is like a little bit like this. Well, you can tell what'll happen, right? Like this guy will start to spin around, and this guy will start to spin around a little bit too after they collide. In this case, the linear momentum is conserved too. Okay, but linear momentum, or the angular momentum, is not zero. So linear momentum is, in this case, the only meaningful thing when the centers of mass hit are that the linear momentum is conserved. Now there's a couple other ways we can do this. We can also have it so let's say we have a block. It goes this way, and it exactly strikes the center of mass of this bar. Well, in that case, okay, by the way, the friction of this table is zero, so there's no other forces on it. Okay. Well, if it strikes the center of mass of the bar, well, then this bar is no different than this block is up here. There's no difference between them. So they're just going to strike that as well. So that's one way that, in this case, that linear momentum is conserved. I'm going to go back to that example to look at when linear and angular momentum are conserved. Let's go back to, again, we're going to look at this table from above. And we talked about what would happen if we have a block here and it ran into a block this way that was like a little bit off center. And what happened is that this block would again start to spin this way. So it would get some kind of linear momentum that way. There'd be a radius of the block. And you'd get a linear, and what would happen? The other block would probably spin the opposite way. It would go like that. So there'd be a linear momentum there too, or an angular momentum too, and a linear momentum, because this block would probably still go forward, but not as fast, and this block would start to go forward too. So in this case, linear momentum is conserved, and angular momentum is conserved. There are other examples of that as well. If let's say that we took earlier we talked about the bar, like we hit the bar exactly in the center. What happens if we don't? Okay. If we hit it, so if it moves this way and it's slightly off axis. Okay. So that is a case where we have that's a case where this thing will start to spin. Let's say that the point is actually here. This bar will start to spin, probably like this, right? Okay. And this bar will start to go forward too a little bit. So it'll do both things, spin and go forward. This one will probably just go forward. But in both cases, the linear momentum is conserved and the angular momentum is conserved. Now the thing is, how does this thing have an angular momentum? That's kind of a weird thing, but at the moment that it strikes, it does have an angular momentum, but it's compared to the length of this bar. So it does have an angular momentum along there that you could calculate using like the mass of this thing, mv r, but r is going to be like whatever this distance is here, the distance from the center of mass to that block there, not this distance across there, sorry. So it's going to be, you're going to calculate it differently than you ordinarily would. But that's a case where both things are conserved. I want to point out that energy is not necessarily conserved in any of these collisions. It might be, but you can't tell at all. Okay. Now, we're going to look at an example where angular momentum is conserved. And this is like kind of a popular one. Let's say we have a bar. It's fixed at the top. And we have a block. And the block comes in like that and strikes it. Well, in this case, you can see that like it's going to have some kind of that's going to have some velocity this way and a mass this way. And this is going to have some kind of moment of inertia or whatever, and there'll be some radius along this way. Well, you know that the problem is that momentum can't be conserved here, like linear momentum. And the reason it's not is because of this thing here. It's got a pivot, like it's like nailed into the ground or whatever, so it's stopping it from rotating or stopping it from moving forward. So in this case, we actually have something that stops it from moving forward. It's going to stop the linear motion. It's going to actually put an impulse on the bar when you try to move it forward because it's connected to the ground. So that's not going to be conserved. But this bar is going to rotate when it hits it. Okay. That's going to rotate. Okay. And this object and this block may go backwards or it may go forward at a slower motion. But both of them are going to have an angular momentum. Okay. And we're going to compute it over here. And we're going to say that L, the linear momentum, the angular momentum of the whole system, equals the angular momentum after they strike. So it's going to be like mvr plus I times 0, because this isn't moving to start with, is going to equal mv prime r plus I omega. And omega is going to be whatever the new speed of the bar is. And we'll have to do some figuring to find out what some of these things might be. Okay. Sometimes we can conserve energy. Sometimes they give us information to help us figure that out. Okay. We can figure it out, though. But that's how you would conserve that angular momentum to help you figure out stuff about how it spins. And again, you can see that the angular momentum is only conserved because in this case, we don't have the ability to conserve linear momentum because we have something in the way. So we've looked at linear and angular momentum, when linear momentum only is conserved during these collisions, when linear and angular momentum are conserved, and when angular momentum is only conserved. So hopefully you can look at some problems and get a feel for when that applies best.